Okay, we're going to look at two-way tables and conditional probability, and really this is just an extension of classical probability. However, the two-way table is an extraordinarily powerful way to help you with classical probability and a way to organize things, especially when you're working with two variables. All right, we've worked with two-way tables before when we're displaying and describing categorical data, and much of that is going to be the same here. All right, so the outside row and column totals are the marginal values, and we talked about that before. So this would be a marginal value, this would be the marginal value. This right here is always going to be the sample size, or in this case, since we're working with percents, 100%. Okay, and basically when you're working with two variables, I'm thinking a two-way table is probably your most powerful tool, and it's a great ally. I really think it'll help you get a lot of problems that you wouldn't otherwise be accessible to you. The inside table values are your conditional or your joint probabilities, and they're called joint probabilities because they happen at the intersection. Okay, so consider the following scenario. Suppose that 2% of a clinic's patients are known to have cancer. A blood test is developed that is positive in 98% of patients with cancer, but is also positive in 3% of those who do not have cancer. Identify the two variables. Well, so basically what we have here is cancer status, whether you have cancer or not, and the other would be, your other variable would be your test results. So these are your two variables. Now, where you place them really is important. I need to go back to my problem and identify the one probability that is related to only one of the two variables. This one, they set it up fairly nicely. They say, suppose that 2% of a clinic's patients are known to have cancer. So that is associated with only one variable. It's associated with cancer status. It has no relationship to test results. If that's the case, we're going to make cancer status up here. And normally I'm do these fairly rapidly, and I just put C and NC, cancer and no cancer, and positive and negative, just because it's very quick, or I'll use a P and an N if I'm concerned about getting confused. Well, 2% of a clinic's patients are known to have cancer. So that's 0.02. Well, I know it has to sum up to 1, so this is 0.98. I'm not going to go any far. Well, actually, let's go just a little bit farther. Because this is 0.02, I'm going to write 0.02 in small numbers in each one of these squares. And I'm going to do the same thing with the 0.98. I'm going to write 0.98 in each of these using small numbers so that I have room to write a lot more, because I'm going to need to put more information. All right, so let's look at these other variables and make other percents real quickly. A blood test is developed that is positive in 98% of patients with cancer. Oh, but this is positive with cancer. So that is associated with both variables. It's associated with test results and your cancer status. And it's also positive in 3% of patients who do not have cancer. So once again, test status plus cancer status. So consequently, those were associated with with more than one variable. So we always want to find the ones associated with one variable, which in the case was a 2%, which is only associated with cancer status. All right. So that number we always want to put it there. It just makes our life a lot easier. So let's look at this. A blood test is developed that is positive in 98% of patients. So positive with cancer. Oh, so positive with cancer means this is going to be 0.98. And I need to write that small. And I'm going to go ahead and before I go much further, I'm going to say, you know what? Because that's 0.98, I'm going to sit there and go, I need 1 minus 0.98. Right there as well. Okay. And you're like, well, where did you get that? It's just 1 minus that value. So I'm going to go ahead and multiply these out, and I'm going to write them in a little bit larger number. So we have 0.02 times 0.98, and that gives me 0.0196. 0.0196. And I'm going to take 0.02, and this is also 0.02, just happened to be. Normally that won't happen, but it did here. So this is 0.0004. And if I add these two values up, they have to equal 0.02, which they did. So that means I probably did it correctly. Not a guarantee, but probably. Then it also says it tests positive in 3% who do not have cancer. Oh, so this is also going to be 0.03. And this is going to be 1 minus 0.03. And let's go ahead and multiply those out. So 0.98 times 0.03 is 0.0294. Let's add that to the 0.0196. And that equals 0.049. All right. Let's multiply this out. 0.98 times 0.97 is 0.9506. Let's add the 0.004 to it, plus 0.0004. And I end up getting 0.951. Now I should be able to add these two numbers. I should be able to add these two numbers and get 1.0, which I do. All right. So with that said, I can check this table out. This plus this equals that. This plus this equals that. This plus this equals this. This plus this equals this. This plus this equals that. Probably have this table done right just because everything adds up correctly. Okay. So once I have that, I can start answering questions. What's the probability that the test is positive? Well, the probability of positive equals 0.049. All right, so it tests positive 5% of the time. The next thing, what is the probability that the test is negative and the person has cancer? Positive and they have cancer, that's the intersection. All right. What's the probability that the test is negative? I'm sorry, negative and the person has cancer? 0.0004. So probability, and by the way, I knew that I was looking for the intersection because of the and. And tells me the intersection. So I'm looking for has cancer and negative. So the probability of cancer and negative equals 0.0004. So it's pretty good on detecting what if you don't have cancer. I mean, if you it doesn't give a negative test if you have cancer very frequently. It's pretty good about that. Given that the person has cancer, what's the probability the test is negative? All right. So given that they have cancer, so that's given, intersection over given, don't want to forget that. The intersection over given, well, what's given that the person has cancer, what percent has cancer? 0.02. What's the probability that's negative? 0.0004. So 0.004 divided by 0.02 is about 0.02, which is what we anticipated. And then finally, the last question. And the last question is, if a person who's chosen at random from the clinic's patients is given the test and it comes out positive, what's the probability the person has cancer? So, given that it's positive, what's the probability that they have cancer? Well, first off, what's the probability of positive? 0.049. Probability of positive and having cancer is the intersection, which is going to be 0.0196. So let's take a look and see what that looks like. 0.0196 divided by 0.049. And I end up being 40%. And that is scary. Because here's what that means. 40% of the time the test tells you it's positive, you actually have cancer. The rest of the time, you don't. That just ruins some people's day. And if you don't believe me, let's try it out. Probability of, so we ended up, given that it was positive. So given that it was positive, let's look at the intersection. All right, of not having cancer. So this is not having cancer. .0249 divided by 0.4. Oh, excuse me. 0.0249 divided by 0.049. All right. So very, I really would help if I input the right data. You should 0.294, 0.0294 divided by the 0.049. 60% chance. So there's a 60%, the test comes back positive, you think you have cancer, but there's a 60% chance that it's wrong. This is what was going on in the 90s and actually in the 80s. And when doctors were not required to take probability, they didn't understand the importance of it. So they're giving these tests. It seems really good because early detection is important. And this sat there and said, you know what? We catch it. If you have cancer, we're pretty sure that we're going to get it. Matter of fact, so this is, it's like 4/10,000ths of the time do we mess that up. So they're telling people that, and they're like, you know, we do have some false positives, but that's only 3%. So that doesn't sound that bad. It doesn't sound that bad until you sit there and you put it in a contingency table and you find that 60% of the time that you told someone that they had cancer, they don't. All right. So this is the power of the contingency table, and extremely important. The main thing you have to do is you have to sit there and go identify your variables, which in this case was cancer status and test results, positive or negative, and determine which one of the percents is associated with only one variable. In this case, the 2% was associated with cancer status. That went here, and from that point, we can build the rest of the table. You can always check by multiplying and adding. All right, this plus this has to equal that. Rows and columns must sum together, and this gives you a lot of power in solving conditional probabilities and with classical probability, as you will see here in a little bit. Thank you for watching.